In this video, we are going to see about ceramic implant materials. Okay, although the use of ceramic materials is well known in dentistry, their use in medicine as implants is relatively new. The main advantage of ceramics over the other implant material is its inertness, that is, the property of not able to react with other compounds or elements, or its biocompatibility. It's friendly with our body, it does not create any negative reactions to the body because of low chemical reactivity. However, certain ceramics are made reactive so that it will induce direct bonding to hard tissues. So hard tissues means, right? Hard tissues are bones. Some ceramics are also made to be absorbed in vivo after their original function is fulfilled, right, for a reabsorbable material. Carbon implants have been found to be especially useful for blood interfacing materials such as heart valves. They are also used as a reinforcing component of composite implant material, right? When we mean by composite, it means combination of one or two materials. So composite implant materials, due to their specific strength as fibers and their excellent biocompatibility property. Coming to the class of ceramic materials, that is aluminum oxides. The main source of high impurity alumina is bauxite and native corundum. The commonly available alumina can be prepared by calcining alumina trihydrate, resulting in calcined alumina. Tabular aluminas are massive low shrinkage forms that have been sintered without adding permanent binders. It's also possible to obtain 99.9 pure alumina. It's available from company Linde Co. prepared from ammonium alum. However, the ASTM requires only 99.5% pure alumina and less than 0.1% of combined silicon dioxide, alkali oxides, mostly sodium oxide for implant. Alumina has a rhombohedral crystal structure, that is, its A value is 0.4758 nanometer and C is 1.2991 nanometer. Single crystal alumina known as sapphire and ruby, depending upon the types of impurities added, like Fe, ferrite and Ti for sapphire, chromium for ruby, has been used successfully to make implants. The single crystals can be prepared by feeding fine alumina powders onto the surface of a seed crystal, which is slowly withdrawn from the electric arc or oxyhydrogen flame as a fused powder builds up. Alumina crystals up to 10 cm in diameter have been grown by this method, and the bend strength is calculated SB of a polycrystalline alumina with constant grain size can be expressed as SB is equal to S naught, then exponential minus BP, where S naught is the bend strength and at zero porosity, B is the constant and P is the porosity. Right, then zero porosity strength is given by following equation. Before that, I think you are aware about what is meant by porosity, right? Porosity means the pores, small holes on the material. So zero porosity strength is given by following equation. S naught is K d to the power 1 by 3, where K is a constant and D is the grain size. that is the size of that pore. When porosity increases, what is the disadvantage, right? When porosity increases, the strength reduces. Okay, so you can see in this graph the relationship between the grain size and porosity for full dense alumina. From this graph we can understand that what is happening to increase in porosity, right? When porosity is increasing from 0, 1, 2, we can see that the grain size is reducing, right, from 140 up to 20. So when porosity increases, the grain size is decreasing. Grain size versus porosity of highly pure, fully dense alumina. When the porosity is below 2%, the grains become much larger. When the porosity is low, the grain becomes much larger, which will, according to equation 1, will decrease its strength. The size of grains can be kept below 2 parts per million by adding 0.1% MgO. The addition of MgO will make alumina almost translucent, so that it can be used even for housing sodium vapor lamps. Okay, this type of alumina has not as yet been used for implants. Alumina in general is quite hard. Its Mohr number is 9 compared to 10 for diamond. Its hardness varies from 2000 kilograms per millimeter square to 3000 kilograms per millimeter square, and hence it is used as an abrasive and bearings for watch movements. This high hardness combined with low friction and low wear are major advantages of using alumina as a joint replacement material despite its brittleness and difficulty in fabrication. It is of great interest whether the inert ceramics such as alumina can be fatigued in either dynamic or static conditions. In one study, it was shown that the fatigue strength of alumina can be decreased by presence of water above critical stress. This decrease in fatigue strength is due to the delayed crack growth, which is accelerated by water molecules. Okay, so we will see a small analogy question. Analogy means in the question you will be having some relationship between two words, and you need to find out what is the relationship given in the option. Okay, so odometer is to mileage as compass is to what? Odometer is to mileage as compass is to, the correct answer is direction. In the question it's given odometer. So odometer, why we need odometer? To measure mileage. So compass is to know the direction. It's a small analogy question for you. Okay. Another question. Marathon is to race as hibernation is to, is it winter or beer or dream or sleep? The right answer is sleep, because in question it's given marathon is to race. So marathon is something related to race and hibernation is related to sleep, because marathon is to run slowly in race. So hibernation is sleeping for a long time. You could have heard that some animals hibernate for years together underground, right? Okay, thank you for seeing this video. In the next video lecture we will see about another biomaterial. Thank you.